Swayam Prabha. Digital India. Educated India.
Hello, welcome back. We'll continue our discussion of the linear instability analysis of a two-fluid interface. Let's quickly recap what we've done thus far. We're looking at the stability of an interface formed between two fluids. Say I have a fluid of density rho 1 superimposed over another fluid of density rho 2. The fluid of density rho 1 is moving with a velocity u1, the fluid of density rho 2 is moving with a velocity u2. Rho 1, rho 2, u1, u2 are all constants. We started with our basic governing equations and boundary conditions, and we quickly substituted this base flow given by rho 1, rho 2, u1, u2 into the governing equations plus the boundary conditions to check that it satisfies the equations, as it does. Then we introduce a small perturbation to this base flow field, which we denoted by the primed quantities ui prime, vi prime, pi prime, etc. And we substituted the perturbed flow fields into the governing equation and boundary conditions and linearized the flow. So, the first step was to linearize the flow field about this perturbation, about this base flow field. Okay, so, that gives us a set of linear partial differential equations that will describe the growth or decay of the perturbed quantity. The next step that we followed was to assume a particular form for the perturbed quantity called the normal mode form. We wrote these in equations 14 to 16. And we are now at a point where we know we have our linearized governing equations in equations 8 to 10 and the normal mode form in equations 14 to 16. So, we begin by our solution process allowing us to substitute when we perform this substitution. What we get we get these three equations, the first one coming from the continuity equation, the second one from the x momentum equation, and the third one from the y momentum equation, just for our reference. The double prime quantities are only functions of y, just so we recall, and that is the reason the derivatives of the double prime quantities with respect to y remain, but with respect to either x or time are simply converted into an algebraic multiplication with either ik or omega. or as the case with the advection term omega plus I k u I. So, from these equations we are now able to, we want to get a single ordinary differential equation if we can for p I double prime by eliminating u I double prime and v I double prime. So, let us see what that process looks like. So, we are able to write down u I and v I. U I double prime is minus I k over rho I times p I double prime divided by omega plus I k u I, and v I double prime from 18 or from 19 is given by this. Now, I can use these two equations and substitute into 17. So, in order to do that I need to take the derivative of the equation for v I double prime with respect to y, and that is what I have done here. Now, when I substitute the equation, substitute this equation and this equation into (17) here, which is what we got from continuity. Okay. So, for in short I can write this as This is our equation 20. Now, remember I equals 1 or 2, we have maintained that notation all the way through from the beginning of this derivation. So, essentially P1 and P2 are the static pressures in fluids 1 and fluid 2, and they are independent, they are separate. So, I am going to solve for them separately, and from there I will find okay. So, that is our location of the two fluids 1 and 2. 1 is located in the region y greater than 0 and 2 is located in the region y less than 0. So, this is the most general form of the solution of equation 20. Now, if you think of fluid 1 for a moment, for all y greater than 0, and remember k is a positive number in our temporal linear instability analysis, k is a positive real number. So, if k is a positive real number, then this first term here C11 e power ky is going to become increasingly larger as y increases. But the static pressure in fluid 1, especially noting that these are all little p, these are all lowercase p, meaning they are perturbation quantities. The perturbation quantities have to remain bounded. So, for the perturbation quantities to remain bounded and this to be the solution, the only possibility is that C11 has to be 0. C21 not being 0 is okay, because the e power minus ky function decays away exponentially for all y greater than 0. Okay. So, C21 does not have any constraint on it, but C11 has to become 0. Similarly, using similar arguments for P2 double prime y and noting that fluid 2 is located in the region y less than 0. So, if y is less than 0, k still being a positive number, e power ky is going to decay exponentially as y becomes an increasingly negative number, that is y goes from minus 2 to minus 3 to minus 100 etc. As y becomes an increasingly negative number, e power minus ky is already bounded, but that is not the case with e power ky is bounded, but that is not the case with e power minus ky. E power minus ky now becomes unbounded. So, therefore, in order for the whole static pressure to remain bounded, C22 must be equal to 0. So, now we are in a position to write down the general form of the static pressure in fluid 1 and 2, which is our single primed quantity. From here, now we already have a relationship between ui and pi prime, ui double prime equal to minus ik over rho I times pi double prime divided by the omega plus ik ui. So, using that we will be able to write down what ui double prime and is supposed to be. And similarly, I can write u2 double prime. I am not going to write it down, but you can see that once I know u1, u2, and I can also use the other equation. I can use this equation to get to what V I prime would have to be. So, now that we have u1 and v1, let us also write down and v1 double prime would be analogous, v1 prime would be analogous. So, now we have the flow fields and we have two undetermined constants C12 and C21. So, let us quickly take stock of that. And we will use the two boundary conditions that we have, the kinematic and the dynamic, two sets of boundary conditions, the kinematic and the dynamic boundary conditions, to calculate a value for C12 and C21 such that we have a non-trivial solution for the problem. That is our goal. We do not want C12 and C21 to become 0, because if they become 0, then we are left with the trivial case that the base flow alone persists. We want to introduce a perturbation and study whether the perturbation will grow or decay. For that purpose, we do need C12 and C21 to remain non-zero. Okay. So, let us now write down our kinematic boundary condition. Just to recall, a kinematic boundary condition is basically a requirement that if I have a fluid particle on the interface. So, if I have a fluid particle sitting on this interface, that fluid particle remains on that interface at all points in time. So, if I have a meniscus kind of like that, and if this fluid particle is sitting here, whether the fluid particle is translating in whether the movement of the fluid is to the left or right or up or down, the fluid particle is not detached from the interface. That is pretty much the physical meaning of what we call our kinematic boundary condition. So, let us write that down. What that says is V1 prime evaluated at y equal to 0 Okay. We have the same normal mode perturbation introduced to eta. Eta happens to be the actual physical perturbation that you have introduced to the wave. So, if you have eta to be of some having some amplitude eta naught and some temporal frequency omega, like we have said before, and a wave number k, then the requirement that the y direction velocity in fluid 1 V1 prime as we approach y equal to 0 from fluid 1, which is basically denoted by this quantity V1 prime at y equal to 0 is equal to the physical movement of the interface or physical movement of the interface in an advected sense. So, dou eta dou t plus u1 dou eta dou x is basically an advection of that interface with a velocity u1. u1 happens to be the fluid velocity, the base flow velocity in fluid 1. So, once we figure this out, now substituting what we have for V1 into this, we get k times C21 So, simplifying we see k times C21 equal to rho 1 times omega plus I k u1 squared times eta naught. Similarly, then we have another kinematic boundary condition requirement for fluid 2, and from there we have essentially the same requirement, but written now from the sense of fluid 2. Now, substituting what we have for V2 prime in here, we get minus k C12